Before we jump into the 4 examples, I think it's useful to look at this function notation and make sure you really understand what it means. It's an easier task to look at a graph and decide if it is even, odd, or neither than it is to algebraically decide without looking at a graph. So we have to look at function notation and understand what it's telling you to do. So f of negative x, remember what that means is that you're inputting a negative x value. And then f of x is telling us that we're getting out a y value. So think graphically. If you were to have an even function that would have y-axis symmetry, then f of negative x means I'm inputting a negative x value. So say my negative x is part of this coordinate. And then what I'm getting out is a y value, which would be the same y value as if I had put in a positive x value. So inputting a negative x gives the same y value as inputting a positive x. That shows that this function is even. So to be an odd function, I'm going to start the test the same way. I'm going to input a negative x value. So take a look at an odd function that would have origin symmetry. So if I input a negative x value, then I'm going to get out the opposite y value. So think of this negative out in front. Think of using the word opposite. The opposite of f of x. I'm going to get out the opposite y value. So my coordinate, if I'm inputting a negative x, I'm going to get out a negative y. That's the opposite y value from what I would get if I had put in a positive x value. So your test starts the same way for even and odd. You always begin by inputting a negative x value, and then you look at what you get out. If you get out a positive f of x that's the same as the original function, then it's even. If you get out the opposite of the original function, then it's going to be odd. All right, on to our examples. Number 1, f of x equals the cube root of x minus x. And we want to determine whether this is even, odd, or neither. So we begin by inputting a negative x. We're computing f of negative x. So that means we would have the cube root of negative x minus negative x. And now we're going to simplify this function and then compare it to the original. The cube root of a negative number will be the opposite of the cube root of x. Okay, think about the cube root of negative 8 would be negative 2. That's going to be the opposite of the cube root of positive 8. And then subtracting a negative x will give us a positive x value. So now what we're doing here is comparing this function with our original function. If they're the same function, then it's even. If they're opposite, then it's odd. And if it's neither one, then it's going to be neither. So we have to decide, are these the same function, are they exact opposites, or none of the above? And it turns out that they are opposites. And to see why, you might want to factor out a negative 1. So you'd be left with negative times the quantity cube root of x minus x, if you factor that out. And then compare that with the original, and you can see that this is the opposite of the original function. In other words, this is the opposite of f of x that we were given. And that shows that this function, f of x, is odd. So we say that f of x is an odd function. That's the type of function it is. If I were to then ask you what type of symmetry it has, you would tell me that it has origin symmetry. And to check this, you could always put it on your graphing calculator, take a look at the graph to see if indeed you are correct. But this would be the algebra you would show to justify why this is an odd function. It has origin symmetry. Number 2, f of x equals the absolute value of 2x plus x to the 5th. So we begin the same way. We're going to input a negative x value and then compare our result with the original. So that would be the absolute value of 2 times negative x plus negative x raised to the 5th power. So now we simplify. Well, the absolute value of 2 times negative x will end up being the same as the absolute value as 2 times positive x, since the result is positive in the end. And then a negative x raised to the 5th power will end up being the opposite of x to the 5th. So when we simplify, we get the absolute value of 2x minus x to the 5th, and now we compare. Again, we're comparing it with the original. Are they the exact same? No. So the function is not even. Are they the exact opposite? If you're not sure, then you'd want to factor like we did on the last example. But we can tell that they're not opposites because the x to the 5th, one is positive, one's negative, but look at the absolute value. The absolute values are the same. So these two functions, they are neither the same function nor are they opposites. So this is an example of a function that is neither. It doesn't have y-axis or origin symmetry. It is neither even or odd. F of x equals 2x divided by the quantity x squared minus 3. So to test for even, odd, or neither, we input a negative x. So we'll have 2 times negative x in the numerator, all divided by negative x, the quantity squared, minus 3. And then we simplify. So we'll end up with a negative 2x in the numerator. In the denominator, the negative x, when you square it, will end up just being a positive x squared. And now we're comparing this with the original. Are they the exact same? Well, the denominator is the same, but the numerator is not. So they're not the exact same. Are they the exact opposite? Well, you might be confused by that negative sign in the numerator, and perhaps it's helpful to remember that that negative, you actually could rewrite it out in front of the entire fraction, and this would be equivalent to negative, the whole fraction, 2x divided by x squared minus 3. So then what that tells us is that this function is indeed the opposite. It's the opposite of the original function. And so since they are opposites, that means that this is an odd function. This is an odd function, and its symmetry would be origin symmetry. Number 4, f of x equals 5x to the 4th minus 1 over x squared. So again, we input a negative x and see what our output looks like. So simplify. Again, we've got negative x raised to the 4th power, which would be equivalent to just x to the 4th power. So 5x to the 4th. And then the negative x, once you square it, will turn positive and be the same as just x squared. So we end up with 5x to the 4th minus 1 over x squared, and compare it to the original. Are these functions the same? Yes, they are on this one. They're the same. In other words, what that means is we put in a negative x value. So we computed f of negative x. But what we got out was the actual original function. We got out f of x. It's the same as the original. Therefore, this would be an even function. This function is even. That means that it has y-axis symmetry. In number 5, I just wanted you to think about parabolas, because sometimes there's a misconception that all parabolas would be even functions. So people assume that any parabola would have symmetry over the y-axis. And indeed, if you have a parabola that's been shifted up or down, these parabolas would definitely have symmetry over the y-axis if they're shifted up and down. But remember, we could also have a parabola that's been shifted, say, right or left. So a parabola that's been shifted somewhere to the right or somewhere to the left, it's no longer going to maintain its symmetry over the y-axis, so it's not going to be an even function. So some parabolas are even, but some are not. So you have to be careful. You cannot just look at the exponent to determine whether it's an even or odd function. You actually have to either look at the graph or do the test. Even functions, when you input a negative x value, you'll get out f of x, the same as the original function. And odd functions, when you input a negative x value, you'll get out the opposite of the original function. That's how we're going to determine whether they're even or odd algebraically.